In OChem, we tend to think about reactions and reactivities and mechanisms and all that fun stuff. And it would be nice if there was some kind of rule set that we could at least use most of the time to help us predict and figure out how reactions occur. So before we get into those potential rules, or at least this author's interpretation of them, it is helpful to recognize that there are categories of reactions that we need to understand and be responsible for. And so those categories of reactions are listed below. So if you're listening to anything else within my video sets, you may hear reference to the 5 types of reactions. What I'm referencing are these 5 types of reactions. Acid-base reactions, exclusively Bronsted-Lowry, substitution, elimination, addition, and radical. Each of these had different mechanistic elements within them, but for the most part, these are your primary categories. Everything else is now just a blend of these reactions. Okay? So the next part would then be to decide, how do we know where we're moving within this? And that's ultimately getting at our reactivity. Okay, so our reactivity of things, we would hope there are some kind of rules. The biggest kind of driver behind almost all of our chemical reactions, if not all of them, is stability. Okay, and at least for the first 4 on our list of reactions, we're always going to try and minimize charge. So if a reaction is going to proceed forward, it needs to minimize the charge somehow. It doesn't have to happen immediately, but it's going to try to minimize it. Okay? So what we want to go through and do is consider how we place a charge on an atom that can hold the charge better. Well, how do we know it's better? Okay, that better has to do with these rule sets. They're now all listed out here. Okay, if you go online, there's a variety of other acronyms. I've heard a common one is CARIO. Okay, I have no idea what the O is, but we get charge. That says charge, I promise. And then atom effects. Well, which atom effect? Because there's multiple. Resonance. And induction. So this kind of works as a nice overview of all the rules, but it doesn't provide enough nuanced detail within it. So while it might be neat to have some fancy little mnemonic device to memorize it, ultimately you need a little bit more detail. And that's where I would go through with the detail listed in the list that I've got. Okay. So my list is going to equally start with charge. So this is an atom effect. I want to look at the atom that holds the charge. Well, what is the charge? It doesn't matter. It can be positive, it can be negative. So that's where knowing definitions of reagents can help out. And we'll look at those in a second. So the first thing we want to do is look for charge. After charge, we want to look at the atom that holds said charge. Okay, what is its size? And the reason we look at size first is that size tends to be a larger dictator of stability than electronegativity, which is the next one on the list. There are some conflicts there, but for the most part, size drives reactivity. Okay, so size is a larger effect, no pun intended, than electronegativity. After that, we've now kind of used all of our primary atom effect things, or obvious ones. So because we can't use the atom anymore, now we'll step out to the molecule. When we move out to the molecule, we can look at a molecule size and a molecule electronegativity. These are in quotes because what these are trying to reference is that we're actually using the exact same principles that we used for the atom effects. However, it's not size and electronegativity that's ultimately going to dictate it. It's actually resonance and induction. Okay? Having a larger molecule doesn't necessarily do anything if the electrons can't move to the other parts of the molecule. That's resonance. Okay? And because the electrons are actually able to move, that's a larger effect or a more important effect, okay, than, say, induction. Well, what's induction? Induction is now saying there's a really electronegative element somewhere in the molecule, and that then pulls on the electrons, okay, causing them to move into the structure towards that electronegative element. Okay, this is a weaker effect because the electrons don't actually move, but they're drawn towards. Okay, so in one case, resonance is the electrons moving from atom A to atom B. I've got electrons here being able to jump into a place where they can interact with atom A. Okay, that would be a resonance system. If our electrons were envisioned as kind of like eyeballs, okay, in the inductive effect, what we're saying is that those eyeballs are looking towards atom A because atom A is more electronegative. They aren't moving towards atom A, they're just looking. Okay? That changes how they interact with the outside environment. For instance, if you're looking at the computer screen, you probably don't see that guy in a scary mask sneaking up behind you right now. Okay? That changes your environment. After that, we then move into the O part of CARIO that I have no idea what it meant, so I made something up. Okay, and because I can't say bad words, everybody asks, I made it CARP. This is where you run into these kind of smaller effects that still contribute a lot and ultimately tie back to aspects up above. Okay, this is where you'll see hybridization effects, and kind of substitution effects that we'll look at here in a little bit. Okay, so then how would we use this? Well, we could use this for our Bronsted-Lowry acids. If I had HF versus HI, we could ask the question, well, which of those is the stronger acid? Okay, how do we do it? Well, the first thing we would do is evaluate the conjugate base. Okay, because it's an acid, it donates the proton, and we get F minus, and we get I minus. So we can now compare F minus to I minus. Well, they both have the same charge, so that's a null explanation. What about size? Well, fluorine is much, much smaller than iodine, which means that extra electron that's in there on iodine can now be anywhere in the molecule or in the atom, which means it's more stable. Think about you being confined in a 5x5 square versus the planet. Okay? This is why jails are a punishment. You're confined to a smaller space. Okay? That's also why most people in jail are a little punchy. Okay? So we're using the rules to help us apply how these things work out. Okay? And what we're concerned about is that stability. Okay? In the case of the acid, I'm saying I minus is more stable than F minus. If I minus is more stable, that reaction is more likely to occur, which makes that the stronger acid. Okay? HI, the stronger acid. So it allows us to kind of manipulate through this, but we have to know the definitions of what these things are and how to kind of piecemeal our way through it. Okay? Well, what if we switch to the harder one? Because if you're in first semester, you'll likely see acids as our rankings for stabilities. If you're in second semester, you're going to have to evaluate bases. Okay? And because first semester is primarily acids, when we get to second semester, everybody freaks out and can't figure out bases. Well, it's the exact same idea or concept behind this. Let's take a look at hydroxide versus amide. Okay. Well, which one's the stronger base? And this is where people will go through, I got to evaluate the conjugate acid. Okay. You could. It's not necessarily wrong to do that, but why are you doing that becomes the larger issue. Okay? Remember when we looked at the acids, the whole point was to make a charge appear so that we could see it and evaluate it. If we look at the base situation, didn't we start with a charge? Well, yeah. So let's not change it. Let's just stick with that charge. Okay? The next part is, what does a base do? Well, it donates electrons. Okay, well, the one that's more negative, the one that's more able to donate those electrons is going to be the stronger base. So we compare the atom charged, oxygen versus nitrogen. They're both negative. So that's a moot point. Size, within a row on a periodic table, there's very little size change, which means size is a moot point. The next one is electronegativity. Yes, there is a significant difference in electronegativity. Oxygen is more electronegative. Chi is our symbol for electronegativity. Well, what does that mean? Okay, if it is more electronegative, it's holding its electrons, okay, which makes it less effectively negative, because that negative doesn't see the world, it stays on the oxygen, which means the nitrogen is actually more negative, not electronegative, it's more negative, which makes it the stronger base. Same rules applied differently. Why do we apply the rules differently? You're not looking at an acid, it's looking at a different thing. Okay? We can also do it with electrophiles and nucleophiles, just like with acids and bases. Electrophiles, we want to find the most positive atom. So look for ways that the electrons in the structure can move around to generate a positive charge. Sometimes your electrophile will be positive. Well, that's a pretty good red flag that that's the electrophile. Nucleophiles tend to be the trickier one. That's looking at your most negative atom, but that's ultimately the same thing that we did with our bases. Okay, so the idea is to use these rules every time you're attempting to come up with a reaction. Okay, so let's take a look at the bottom one, our other stuff category. So if we take a look at these three species, what makes them unstable? Well, number one, we have a cation. It's positive. That's unstable. Number two, we have a radical. Okay, that's unstable. It's not charged, but it's unstable because we have that floating electron. And the last one, we have an anion, and it's negative. Okay, well, each of these has slightly different characteristics, and we would have to evaluate those characteristics at each and every single step of the way. Okay, because they're all different from each other, what we're going to do is focus on just that cation. Okay, well, it's unstable because it's positive. Well, what other cations could there be? Oh, well, there's a bunch of cations. What's the difference between these cations? If we use our rules, charge, they're all charged. That charge is on a carbon, which means the other atom effects are null and void. We can move to resonance. There's not enough of the structure in each of these to be able to say that resonance isn't a factor. Same deal with induction, okay, which leaves us in that O-carp category. Okay, so what is our effect? I would argue that this is what is known, in my point, as a substitution effect. Okay, in this substitution effect, what we're looking at is the difference between each of these. Hydrogen versus hydrogen. Well, there's no difference. Versus hydrogen, there's still no difference, Mike. This is kind of dumb. Oh, versus carbon. Okay, well, what's the difference between carbon versus hydrogen? Well, carbon has more electrons. Carbon has 4 valence. Hydrogen only has 1. Okay, so that would suggest, all things being equal, that our bottom one has more electrons around the positive. Well, what makes the carbocation unstable? That it's positive. How do we stabilize it? Make it not positive by giving it electrons. Well, the bottom one gives it more electrons. Okay? And we can run this argument through with each of the other positions around the carbocation, and we'll end up coming to the conclusion that our tertiary substrate is the most stable. Okay? That's neat. That's useful. That's a substitution effect on our reactivity. Okay? In the interests of time, what we're going to do is take a look at radicals very quickly and anions very quickly, okay, and give you quiz questions. So radicals are kind of the in-between state between a cation and an anion. Based off of studies that have been found in the literature, radicals most closely approximate cations. So that means when we look at hybridization, okay, and reactivities, radicals' reactivity mirrors that of cations, okay, or copies that of cations. Okay. After that, we've got our anions. The anions have drastically different chemistry because they have more electrons. Okay. So how does that affect which one's more or less stable? We looked at it with the cation. Think about it and answer this question about it with the anion. And with that, thank you for watching. I appreciate it, and we'll see you in a few.